Are we live? Are we live? Looks like we're live. Hello everyone and welcome to yet another Zosin session. How about it? So let's make a little bit of an announcement and officially start the stream. So just a second. Yeah, so this is going to be a Red Circle live on Twitch. And what are we doing today on twitch.television? Today we are playing with the Rust macros. How about that? https://twitch.tv/tsoding. And I'm going to ping everyone who's interested in being pinged. And the stream has been officially started. Stream has been officially started. And we've already got subs. Thank you, Nelete, for 3 months of tier 1 subs. I got an invoice about an unsuccessful subscription, but got this sub anniversary message. Seems like a bug. Well, it is what it is. Thank you for subscribing anyway. So yeah, hello everyone. Welcome. So yeah, don't feel obligated to subscribe to me. Though recently I just realized that you can get a voice in Discord by subscribing, even though I don't get anything from subscriptions anyway. So subscriptions kind of became like a more of a moderation tool rather than the income. So I don't know, I'll have to probably do something about that. In any case, so today we continue working on knock, which is basically not cock. It's a simple expression transformer, and yeah, so I came up with like a more elaborated example on what it's supposed to do. So this is like a general idea where you can define like a transformation rules that are pattern match against a particular expression, and you can use these defined rules to sort of transform things and you know, maybe prove something or at least demonstrate something, right? So the tool is not designed to be proof assistant, right? It's more of a like you know, transformation tools just to check things around. So and yeah, let's take a look at it. So I actually off screen I moved the example that we developed into a unit test. So now like I check how the entire transformation happens in a unit test. So I can do something like cargo test and it will work. So one thing you can notice in here is that it is actually kind of cumbersome to like define the AST manually, though in the future it's not going to be a problem because we're going to implement a parser that accepts a string and then turns that string into this AST, so you don't really have to do that, right? So you're supposed to use tool, the tool from like a text file or maybe CLI. But for the development purposes, for the debug purposes, it would be nice to have some way to like make it a little bit shorter. You know what I mean? Because it's kind of inconvenient to like define a string literal, then call toString, and then have a vector and stuff like that. So it's just like a lot of like noise, right? And it's really difficult to read. And this is where Rust macros come into play, right? So they allow you to sort of accept a sequence of tokens as an input and transform it into another sequence of tokens. Yeah, so basically code generate. So yeah, if you never heard about macros, I recommend to actually Google them up. Rust macros. So specifically macros by example. I think we're going to be using macros by example today. Right. So things like println, right? So println is a macro, right? So all of the macros, they have this exclamation mark before the arguments to indicate that they are macro, and in their like between parentheses here, they accept a sequence of Rust tokens, and then they get substituted by another sequence of tokens that then gets compiled, gets parsed and compiled as a like, you know, as a Rust expression. So and today we're gonna just develop exactly that. We're gonna try to develop something that will help us to define these expressions a little bit easier, if that makes any sense. So, yesu. Does anyone have any questions? No question, why do we have to call toString? Because this argument is supposed to be of type string, but the string literals are not of type string, they're of type of string slice. To convert a string slice into a string, you have to call toString method of string slice. That's why you have to do that. So hello everyone, welcome. How are you guys doing? So we got a raid from Togglebit. Thank you so much for the raid. Hello everyone who came here from the raid. What's the difference between macros and functions? Macro is a compile time function that accepts a sequence of tokens and generates another sequence of tokens, and function is a runtime procedure, right? That is executed usually at runtime. All right, so yeah. How do we usually define a macro? So the simplest macro that I want to define right now is the one that allows us to easier define symbols, right? Let's actually start with the symbols. You start defining a macro with a special keyword, or maybe it's another macro called macro rules, right? And you define a name of a macro. Let's define a simple macro called sim, right? So it's gonna define a symbol. And then you have to define so-called macro rules, right? Essentially like patterns that are going to be used to match a sequence of tokens. So they usually look like this, right? So they allow you to match one particular thing or repeating thing. In our case, the only thing I care about, right? So I want to have a symbol and I want to specify just a name of the symbol and not don't provide any string literals and don't call any to string. I just want to provide the thing and it just generates a symbol. So essentially, I want to be able to generate a symbol like this, right? So this should expand to something like symbol a to string, right? So something like this is way shorter than this, and this is basically a goal, right? So yeah, so sim a. So here we are accepting identifier, right? So, and I have to define the pattern that looks like this. So I start with a %, right? So the sort of variables within the pattern, the macro rules, they start with a %, like in PHP, right? And then you define a type, and the type of this thing has to be identifier, right? So, and then we basically say that we substitute this entire thing with just like a symbol, then we get a name, and name is an identifier, it is not a string. As far as I know, right, to turn like any expression in Rust into a string, you have to use something like Stringify, if I'm not mistaken. So let's actually take a look at that. So it's going to be Rust app doc, and let me find API. So there was like a macro called Stringify. Yeah, so here it is, it's called Stringify. So thank you so much for 300 bits, Morrigan++. Thank you. Здорово, надеюсь, тебе хороший день. Yes, it is. The day is pretty good for me today, more or less. So Stringify accepts like any sequence of tokens and turns it into a string, as you can see. So let's actually test it out. I think it's a pretty good idea. So I'm gonna just comment it out. And I'm gonna try to print something in here. So I'm gonna do Stringify 1 + 2 + f. Right, so like completely arbitrary expression, right? Completely arbitrary expression, and if I try to run this entire thing, it's not gonna work because I forgot to actually properly call it. So it's supposed to be Stringify, right? And as you can see, it didn't really call f, and f doesn't exist even, right? So it doesn't exist. So, and it didn't evaluate anything here. So what it did, it took the sequence of these tokens, right? So this is a sequence of tokens, and turned it into a string, and then printed that string because we said it like printed. So this is a very useful macro to just like get a string of a particular expression. So let's go back to macro rules, right? So we're gonna do this thing. So here we get a name as an identifier. And what I want to do in here, I want to stringify. I want to turn it into a string. So stringify the name, and it turns it into a string slice. So what I have to do, I have to do toString, right? So, and that should be it, right? And this macro is going to be very useful in the future when we add more like parameters to the symbol. For instance, I plan to also add location within the file, within the source code file where the symbol was defined. And when I define a symbol inside of like Rust, I want the location to be none, right? So here in the future will be like we'll put none in here. Though, as far as I know, Rust allows you to specify the location within the Rust source code, right? So there are such macros as file, which gives you the path to the current file, right? So you can actually check it out. So println, something like this. So this is going to be something like this, current file, right? So macro rules. Let's actually do something like this. Yeah, there we go. So current file is src. So then you can also have current line, and this is going to be just like literally line. Maybe, so if I got a semicolon in here. Yeah, there we go. So the current line. So essentially you can get the location within the source code of Rust. So, and if we're gonna add the location for the expressions, right? So, and if the expression is defined within Rust, we can just use these two macros to specify the location within the Rust source code. So it's gonna be actually very, very useful. All right. So, yeah, but for now it's going to be just like this. So here we have a symbol macro and we can test how it works. So if I do something like this, right, I'm going to say, please define a symbol A. Right, and it didn't really work because why? So not in a scope. Okay, so I have to do something like expression symbol. There we go. So as you can see, right. I no longer have to like define sim to string. Right, if I try to do something like this. Right. So symbol A to string. Right. And of course it has to be something like this. So it's going to be expression like so. And yeah, there we go. So this is much shorter than this, right? So, and that's basically the goal in here, right? To actually like simplify this entire thing. So, does anyone have any questions so far? All right, so no question. Cool. So let's go ahead and like try to substitute the current symbols with the macro, right? So like this kind of stuff. Like this. So as you can see, it already becomes much shorter. So now if I try to actually, I should probably do test, right? So just to check that the tests pass. As you can see, tests do pass. Everything seems to be okay. So if I replace it with C, it's supposed to actually, well, it probably will still work, but okay, so it doesn't work, so which is fine. Right. Okay. So for the rest of the stuff, we're gonna just like go ahead and replace these symbols with that. I should have actually did it like that. And there we go. So it actually becomes much shorter, and it's gonna become even shorter if when we introduce like the fun macro as well. So where is another symbol? So here it is. So we're going to use a little bit of a Emacs magic to achieve all of that. The tests are passing, and there you go. So this is going to be something like this, and then a boom, and there you go. So this entire thing became much shorter, but we still have a pretty cumbersome fun construction, right? So we want to have something like fun, right, where I also can specify the name of the functor, right? And it would be kind of nice to actually not define like a second argument as a vector, but just like provide the arguments of the functor like they are, like symbol A, then symbol B, and so on and so forth. And these arguments are going to be collected into a vector and just constructed properly. So you know what I mean? So let's actually try to do that. So this is going to be macro rules, and this is going to be a functor. So in here, we're going to try to get the name of a functor, right? So it will accept identifier. So after the identifier, right, so we're going to have a semicolon, right? Not a semicolon, but a comma, right? So we have to put the comma in here. So first comes the name and then the comma. And then we have a sequence of other expressions, right? So the sequence of the arguments, right? If you have repeating things, right, so you actually do it like this. So you expect an expression. And if you want to say that this expression is repeating, you wrap it with this parenthesis and say, okay, this thing is repeating. But then you can say that it's repeating and it's also separated with a comma. Right, so this is a special syntax for repeating groups of tokens. So if you take a look at this macro by example, I really recommend to read this chapter of the Rust reference, right? Because it actually has the syntax. So here it is, right? So we have a macro match, and then you wrap it in this parenthesis with $, and then you specify what is going to be the separator, right? So you have a repeating group of tokens, and then you can specify what they are separated with. In our case, they are separated by a comma, right? And then you specify macro repetition, and the macro repetition is one of these things, which is a star, plus, or a question mark, which are the same like in regular expressions, right? Star means 0 or many, plus means 1 or many, and question mark means optional, right? So 0 or 1. Yeah, it's just like regular expressions. So, and essentially, when you refer to args, you refer to sort of array of groups of tokens, right? And essentially, you can then pass it around to other macros, or maybe expand, and so on and so forth. So, and you say that the first thing is going to be the identifier, as you can see the name, and then a sequence of expressions separated by the comma, right? So exactly what we have in here. So, and this is how you describe all of that within the macro rule, right? So, all right, let me see. So, and how we're gonna basically expand it? What we're gonna expand it to? We're gonna do expr fun, and here I'm gonna specify the name. But the name is just a symbol, is just identifier. I have to stringify it, right? I have to turn it into a string literal. So after I turned it into a string literal, I have to convert it to a string, right? And after that, I have to collect all of the arguments into a vector, right? So I'll have to take the args, right? And since they are repeating, I have to sort of spread it. I think this is how we call it. I'm not really sure, but like in C++, it's usually called like spreading the arguments. And you do it like that, right? Essentially, you take the repeating arguments and then you say, okay, just spread them, but also separate them by comma. You see, when I matched it in here, I said that they're going to be separated by comma. And when I spread it, when I pass it like even further, I can also say that they're separated by comma, which means that I can say that they could be separated by something else, right? I can match them as a comma separated, but then I can pass them as semicolon separated, right? So you basically can customize the separator when you like pass it around. In our case, we don't really have to do that. I can just like put a comma in here and it will work. So I'm not 100% sure on how exactly this works, right? So please correct me if I'm incorrect, but this is how I understand the macros in Rust work. I'm not really proficient with Rust macros. All right, and that should, I think, work. Let's actually try to compile this entire thing, and it seems to be compiling, but this is because we never actually tried to run this macro, so let's actually give it a try. So here is the symbol, right? So, and if I try to run this entire thing, as you can see, it is a symbol. Then I want to wrap it into a functor f, right? And that should be sufficient. There you go. So it actually worked. And then I can say, what if I want to have like several arguments in here? So f and b, and as you can see, it works. Right. Since I also implemented display for the expressions, I can actually print them as like, you know, as something like this, as something that is more human readable. So, and as you can see, this became much, much shorter. Right, it is much shorter than like directly constructing this entire thing. So actually, you know, tucked all of this boilerplate under a macro. Interesting enough, I think it won't work if I don't have any arguments. Yeah, it doesn't work. So because it expects, yeah, because it expects like at least one thing, right? So I'm not quite sure how we can circumvent that. I think I know. So there is an easy way to circumvent that. You can define a separate rule. You can define several rules for a particular macro, right? We can define a rule where there's only identify and nothing else. You don't have any comma in here. I'm not sure. Maybe I can make it like optional thing, but I don't think it's gonna work correctly. So I think it's easier for me to just like define a separate rule, right? Which basically looks like this, where the vector is just like empty. Right, there we go. Yeah, I think it's the easiest way to do in here. And that way it will kind of work. No rules expected for... Oh yeah, I know. So I also have to separate them with semicolons. Yeah, there we go. So now we have a situation when it's completely empty, doesn't have any arguments, and then you also have the situation when it does have argument. Maybe there is an easier way to do that, but I'm too dumb to actually, you know, come up with that. Anyway, so we have a macro that constructs functors, and we can try to apply it in here. So let's give it a try. So here is the pair. Now I can just do it like that. Without any special things in here, right? So as you can see, and furthermore, I can get rid of this vector. So look how more like concise it became, right? It became way more concise than it was before. So, and if I try to like test this entire thing, it should also pass, right? It's passing as usual. And I can go in further, right? So I can just do swap, right? So this is swap. And here I can get rid of the vector, right? So there you go. So this is how it looks like now. It's much shorter. So, and things like vec, right? They are defined like a macro rules. They are in fact defined like a macro rules, and they just expand into creating a vector and then pushing all of the arguments into that vector. In fact, I think it's not implemented exactly like that. There is a little bit of a compiler magic involved in here, but you can think of it this way, right? So the vector actually like creates a vector, pushes everything into a vector, and just returns a vector for you, right? So you can create such macros just to simplify creation of some complicated data structure or something like that. So yeah. All right, so let's continue, and let's actually like migrate all this entire test case to using macros. Right, so it's gonna be something like this, and I'm gonna just remove this entire thing. There we go. So it's much, much shorter. Does anyone have any questions? Maybe. Thank you, Akuna Akwe, for 4 months of Twitch Prime subscription. Thank you, thank you, thank you. Thank you, everyone, for the support. All right. So what we're gonna have in here? So we need to. So I probably need to do something like this, then something like this, and just like that, So then I'm gonna keep using Emacs magic to simplify things around. Lil Bime, I hope I pronounced your nickname correctly. Thank you so much for 2 months of tier 1 subscription. Thank you, thank you, thank you. And welcome to our epic Rust Club. Yes, that's what it is. It's a Rust Club. But you didn't expect that shit to happen. Alright, so we have something like this. And then I am pretty much ready to remove this thing. I hope I didn't fuck it up too much, right? I think everything seems to be fine. Oh boy, okay, cool. So this is another swap. Then I'm gonna do something like this, and we are removing this thing, and then boom, removing the vector, right? And I'm removing that. Cool, look at that, look at that. It became much simpler than it was before. The last thing I need to do in here is probably this one, right? So I'm removing that, and I also need to remove this specific vector, and there you go. So it's much simpler now. Right. All right. So, and we have to repeat that for the expected expression here as well. So, yeah, let's go ahead and do that. So maybe for now, I'm gonna just do it like that. And then I'm gonna remove that, and then just that. Cool. Boom. Now for the pair, right? So it's gonna be something like this. Oh shit! Fuck! Why it was so weird? Okay, so it's gonna be now like this. And like that. And you can remove this thing. Cool. And now this is gonna be this stuff. And I'm going to remove this thing. So yeah. Hopefully it still works, and I think something got fucked up. So unused import, okay, that's fine. And for the tests, so I don't quite understand. What do you want from me? Consider adding COG test. What? Excuse me? What is it talking about? I don't understand. Unused import. Okay, so we have unused import. I can probably remove that. So, and the second problem, really? That was the only problem? I think I'm going crazy, but wait, this is so weird. How is that? Oh, it's not an error, it's a help. It's just Emacs actually called it. Okay, I see. It's just Emacs decided to call it like a red, and I thought it's an error or something, but yeah. So yeah, you can define macros that look like this, and it's a little bit more bearable to work with. But here is the interesting thing about the macros. Right, before I go into that thing, let's actually commit whatever we have and yeah, push that into the repo. Right. So add macros to construct expr AST, right? And I'm going to push that right into the repo. You can find the source code of the thing we're developing in here. I'm going to post it in the chat, and if you're watching on YouTube, you can find that in the description as well. So the cool thing about macros is that they work on the level of tokens, right? As already said, it tries to match a sequence of tokens, right? So that means we can actually put pretty much any combination of tokens between the parentheses in here and then generate something out of them. So that means we can even put like entire DSLs, domain specific language, into the macro, right? And it would be kind of nice to have some sort of like a special macro, right? That essentially, where you can essentially put like an entire expression of knock, right? For example, I want to define swap pair A and B, And I want to define a macro that literally parses the sequence of expression and produces the expression AST. Right. So this is a little bit better than we had before, but something like this would be even better, right? So imagine that you can replace this entire thing with just expression, right? Then swap pair A and B, right? That will be even better, right? Because you can directly just put this thing in here and it's like super convenient. So can we define something like that? In fact, we can, because you essentially can recursively call the macros, right, to actually sort of process the sequence of tokens, right? You can match the sequence of tokens and then match the rest of the tokens and then process them with a different macro, and you can sort of define like iterative process that basically processes everything. So the only thing we need to do is just define such macro. So let's actually give it a try. So this is sort of like a lightweight version of, you know, AST construction macros. So now we're going to try to implement something more sophisticated. So let's try to define expr A, right? So for just a single identifier, we want to construct just a symbol, right? So we want to construct just a symbol. Let's give it a try. Macro rules, right? So macro rules, and here we're going to have an expression. And the first rule we're going to try to match is just a single identifier, right? So we're going to have a name, identifier, and here we're going to return what. So we're going to say that this is a symbol. I wonder if I can just like call something like this, right? So let's just give it a try and see. Will that work? I think it should work. I should have actually run it. I think it worked. As you can see, it seems to be working. So what if I now try to have a function call, right? Is it gonna work? As you can see, it doesn't work. It says that there is no rule to match this specific sequence of tokens. So you see, no rule expected this token in macro call. So let me see what we can do. So for that specifically, we can define a separate rule, right? So within a single macro, you can have separate rules. And as far as I know, they're checked sequentially, right? So, and the rule that first applies is being like transcribed, right? So I think the correct term here is transcription. All right, so in here we have something like name, then we have identifier, right? So we have identifier, then we have parentheses, right? So if you just put parentheses in here, you mean that you want to match like literally parentheses as the token, right? If you want to group the sequence of tokens, you have to use the parentheses with dollar. That's why, by the way, we had to put dollar in here. In a different macro, right? Where's the macro? Like here, because here I'm trying to group like a sequence of tokens, right? And I don't mean parentheses as the token explicitly, and because of that, I sort of like escape them with the dollar in here. So I think that's the logic in here. At least I hope so. Maybe I'm wrong. I don't know. But anyway, so here we want to have like a sequence of tokens. Right, but they are not necessarily identifiers and they're not necessarily expressions. So in fact, within a macro, you have several types, sort of speak, right? You have several types. And I think here is the list of different types that you can actually use within the macros. So far, we use identifier, which is just a keyword like name of a variable or name of the function or like anything like that, just to identify. So, but between the parentheses of a function call, we can have like arbitrary tokens that we need to parse yet. We haven't parsed them, but we'll need to parse them. So, and we need to find something that corresponds to just like arbitrary sequence of tokens that we'll need to parse. And that type is a token tree, so-called TT. Right, token tree is a single token or tokens in the matching delimiters. Essentially, you can think of it as just like, you know, a bunch of tokens that are not parsed yet. You can pass those tokens to a different macro that will sort of like process them even further. And that's precisely what we want to have in here. So we have a name and we're gonna say, we're gonna have arguments, and those arguments are token tree. and we can have several of them, right? We can have several of them. They're not separated by anything, because if there are any separators in there, they are part of the sequence of tokens in here, so it doesn't really matter if they are separated by anything or not. And as you can see, I use star in here, indicating that it could be actually empty, right? It may not have anything in here, right? So how are we gonna process that? So I'm gonna say that I'm gonna translate that into a function call, right? So this is gonna be a name, and for now I'm not gonna try to parse any arguments. I just want to see if it's going to work or not, right? If it's going to at least match whatever we have in here, right? So let me try to compile this entire thing, and as you can see, it works. Right, so function call without any arguments gets translated into functor. So I actually want to have several, examples in here just to check that I didn't break anything. Right, so the previous example was just like a. And as you can see, we're already capable of compiling a single symbol and a function call without any arguments, right? It's not a full implementation of the DSL within the macro, but at least it's a start, right? So we have to start at least somewhere. Shalnan, thank you so much for 2 months of tier 1 subscription. Thank you. And welcome back to our epic Rust Club. All right. So the next thing we need to do, can we now combine these two things together, right? Can we combine them? So if I put a in here, will that work at all? And it doesn't work. As you can see, we explicitly said that we're gonna ignore all of the arguments, right? So now we need to parse the arguments, and parsing arguments is actually quite difficult because you can actually have nested function calls. You can have like several different things in here, as you can see. So that means there should be some sort of recursion involved in here, right? So what I'm thinking is that I'm going to define sort of like a second intermediate macro that parses the list of the arguments separated by commas. Right, so if you're trying to parse an expression, right, it's gonna call that argument parsing thing that in turn calls the expression back, and you have sort of like a, how is it called? Mutual recursion between two macros. The first macro parses the expression, and the second macro parses the function arguments, so to speak. Right, so yeah. I think that's precisely what we're gonna do. So let's actually define something like macro rules, and it's gonna be fun args, right? So this is gonna be fun args, and in here we're gonna say fun args, and we're gonna literally pass the sequence of the tokens between the parentheses into that specific macro, right? Something like this. Oh boy, so for now I'm gonna just put it like that, and let me see what's gonna happen. So the missing token in an argument. Okay, so right now we don't have any arguments for the functors, so we need to match a rule when we don't have anything. Right, so the second thing in here, in fact, supposed to be a vector, but fun does not accept a vector, so we may want to actually not use this macro in here. In fact, maybe we're gonna make this macro obsolete, right? So let's actually not use this macro because we're gonna replace them with this new better macro that actually does everything. So let's actually do something like this. I think it's gonna be a little bit better. Okay, so as you can see in here we provide the name, but then we have a vector, right? So we probably want fun arg construct a vector that we can pass into the constructor in here, if you know what I mean, right? So it's gonna be fun args, right? And then we're passing args like so. There we go. So, and that means when there's no arguments in here, we have to return an empty vector. There we go. Okay, as you can see, it works, right? It works. But if we define a function call that has any arguments, right? If it has any arguments, it's not going to work saying that there is no rule for, you know, parsing that specific token, right? So there's literally no rule, right? We need to define it somehow. So let me actually think how we can define such rule. So it's going to be fun args, right? And I suppose we're going to have a pretty interesting pattern. As far as I know, this pattern among restitions is called TT Muncher, right? Do you guys know what it is? TT Muncher. Yeah, incremental TT Muncher. Essentially, it's a recursive macro that has like a list of tokens that it needs to parse, right? It parses like a portion of it, and then it calls itself continuing like processing the sequence of tokens, right? It munches on the TTs. It is a thing in Rust. It's called TT munchers. I'm not joking. It is. Right, if you want to read more about this kind of thing, you can actually read about it in this article. I'm going to put this article in the description, right? So you can go ahead and read about TT munchers. TT munchers, right? And also, I'm going to like also put this thing in the description, macros by example. Right. But essentially, it's not that different from, you know, processing a lazy list in Haskell, right? In Haskell, you can have a recursive function that slowly processes a lazy list, and it pattern matches the head of the list and then just transforms it into something. It's basically like that, but on the compile time in the macro. So that's what it basically is. All right. That's what it basically is. So, okay, let's actually try to specifically implement the situation when you have just one identifier as an argument of a function, right? So let's actually like start very small. So here we're gonna have a name, and this is the identifier, right? So if we encountered something like that, this thing is supposed to return a vector, right? So it returns a vector with a single argument. And I think we can just like use the expression macro to turn this name into a symbol, right? I think this is the easiest thing to do, right? So, yep. So it didn't really work, probably because I forgot to separate by a semicolon, but not really. Not quite sure what the hell is going on. Invalid ident. Okay, so it's supposed to be ident, not indent. There we go. So as you can see, we managed to actually parse this specific thing. Okay, so let's actually make the example a little bit more complicated. What if we have two arguments in here? Right. What if we have something like this? Right. And we don't have a rule for that. We don't have a rule that can parse the comma and continue parsing the rest of the arguments. So let's actually go ahead and implement that. So in this case, in this specific case, we have an identifier, right? An identifier. Then we have a comma, right? We have a comma, and then we have the rest of the tokens that we need to parse, right? So it's going to be something like this. I'm going to call it rest, so it's TT, and we have several of them. Right, so here is the identifier, and here is the rest of them. Okay, so how are we gonna actually approach all of that? This one is interesting. So obviously we'll have to recursively call to expr on the rest of those things, right? So we'll have to do something like this. Right, and actually, I think I'm an idiot. I'm supposed to have that in a function arg. I'm sorry, it has to be in the function arg. Yeah, so I have to do fun args, right? So, and that thing will return me a vector without this thing. Oh shit. So that means I'll have to, so to take this vector, I'll have to take this vector and append the element in front of a vector. That's what I'll have to do. So if I take a look at the vector, can I just append an element in front of the vector? So I have append. So there should be something like insert, and I cannot insert an element at position 0 within the vector, shifting all elements to the right. I think it's a good idea. I think, yeah, append is a pretty cool thing. It basically takes a vector and sort of like drains the vector into another one. So effectively what I can do, right, I can turn that into a block where I define some sort of a vector, like an empty vector. Maybe I can even do something like this. So here I have the name identifier. I can literally take something like this, right? So I have something like that, and then I have a mutable thing. Then I process the rest of the arguments and I append those arguments in here. So if I remember correctly, you have to make it mutable, right? So this is going to be a mutable thing. Right, there we go. So this is a mutable thing, and I can just return this like that. Can I do it like that? I think vec_dec, no, I already have a vector in the definition of the AST. That means I'll have to change AST, and that means I'll have to change all of the code that depends on the AST. I cannot do that. So, all right, so we have something like this. So that will allow me to process a sequence of just identifiers, right? So let's actually give it a try and see. There we go, it works. Look at that. I can now have like several of them. We can even test it like that. So this is going to be just A, and B, and then I can have several of them. And there we go. So that's pretty cool. So you just have a single symbol, then a single function call, then a function call with a single argument, with 2 arguments, with 3 arguments. And as you can see, the macro recursively like processes all of those things. Though we cannot have nested function calls. I cannot have something like that, unfortunately, yet. Right, I can't have something like that yet. Let's give it a try. So it will not compile because it doesn't know how to parse this entire thing. So I think we can also add that as some sort of an exception. So I think we're gonna start with something super simple. Like how can you parse just a nested function call? Right, as you can see, it doesn't know how to do that. Just a nested function call. So we're gonna do it like that. So this is gonna be a name, identifier, and then a function call. To be fair, I can just like literally copy paste this entire thing from the expression, right? So here it is. So this is the identifier, right? So this is a single function call. And then I can probably return I can replace this entire thing with just expression name args, like so. So I literally just replace it like that. So it's going to be taken in here. So this is the expressions, and then I can put them inside of a vector, right? So I'm putting that inside of a vector, and there you go. I should be able to actually process the like nested function calls. Hopefully, we'll see. Okay, so it doesn't really work yet. So I forgot the semicolon. Okay, so we have a nested function calls. Yeah, so we have a nested function calls, but we can't process them in a sequence, right? So I can't have something like K, B. So we can't have something like that, unfortunately. Let me try, and as you can see, yeah, it doesn't know how to process the comma when you have a nested function calls. So now, where is the fun args? Fun args, here it is. So we're gonna do a similar thing to just this, right? I'm gonna take this pattern. So here's the name, then the arguments, and then we have the rest of the things that we haven't processed yet. Right, so we haven't processed those things yet. And then we're gonna just do it like that. So here is the vector. Might as well take this thing like so. And that should be enough, I think, to process any like arbitrary thing. I think it should be enough. Let me see. Yeah, okay, so that works. So we have g of a K of B, and then you have F over this entire thing. To confirm that it actually parses everything correctly, let's actually not use the debug output, let's actually render them back. So here we take in the expressions and parsing them at compile time, right? We're parsing them at compile time, and then we're rendering them back, right? So we're rendering them back, and they look exactly like the original ones, I think. I think they do look exactly like the original ones. So, yeah. Oh yeah, the nested one without the arguments may not work. Yeah, so there's a couple of other cases in here. Yeah, you're right. No, it actually worked, surprisingly. Oh yeah, it worked because you know how we match it? Right, we match it with a star. Right, so it's actually allowed for this thing to not have any arguments, and it's gonna work all right. So yeah, that's pretty cool. And that obsoletes all of the previous macros in here, right? So yeah, there we go. So we have a small DSL inside of this specific macro. TTs have been munched, yeah, exactly. TTs have been munched pretty successfully. So, and now, instead of this entire thing, I can say expression swap pair A and B. There we go. So it's much simpler than this entire thing. It's much, you know, more readable, I would say. So let's give it a try. So now this is how it's going to look like. And I'm actually going to do like a test. So cannot find expression in this. Okay, so I think so where is the export? So I think I have to define this macro before the module, the testing module, for that thing to actually work. So let me try. Okay, so it is passing. So the tests are successfully passing. So then we have expression pair BA. There we go. So the whole point of the rule in here is that you have a head which defines a certain pattern, and then you have the body which replaces based on that specific pattern. And now I can define these expressions just directly, right? So I don't have to, you know, construct anything in a really weird way. I can just like do it like that. All right. So in case of input, what do we have in here? We have something like this. And by the way, you can call the macros with any brackets you want, right? You can call them with curly brackets, you can use like just square brackets, or you can use parentheses. As far as I know, Rust doesn't care, right? You can use whatever brackets you want. So if you want to define something more complicated, you can just like do it with curly brackets. So here we have foo, then we have swap, then we have pair, then we have f of a, and then g of b, right? So that's the first sort of argument of this thing. And the second argument here, as far as you can tell, is pair q of c, z of d. Right, there we go. So this is basically what we have. So this is a pretty complicated expression, and it's way easier to define it like this rather than like this. And we can just replace it like that. So it's much more readable. So this is an input, and in here we're trying to apply this rule to this input to get the following expected output. Let's actually take a look at the expected output. So the expected output is going to be like this. It's supposed to be foo. Then we have to have a pair GB FA. So you see in the original expression we had pair FA GB, but after applying the swap rule, it should become pair GB FA. Right, so this is what we expect in here. And the second one in here is supposed to be Z of D, Q of C, which is basically swapped arguments of this thing, right? So it fucked up something, right? There we go. So, and we can have it like that. I might as well actually even just straighten it up to make it a little bit more readable. I don't know, maybe something like this is more readable because you can see the separate things in here. But yeah, it's much shorter now, right? Remember how it looked originally? So we can actually take a look at the diff. So originally it looked, I already committed everything, but yeah, it looked even more horrible than it is right now. Okay, so let's actually try to run the tests to see if they pass, and something went completely wrong because I forgot to put semicolon. And it's working, right? The tests pass. The tests actually pass, and we can try to break them. So instead of like B, I can do A, and that should break them. And as you can see, it's broken, and it shows you what does not match, even though it's not particularly readable. I wonder if you can make it like print in a prettier way, but I don't know. I need to research that. But as you can see, it is working, so it's actually pretty cool. It's actually pretty cool. And we don't need the symbol macro and the fun macro anymore. So we only need this thing that basically compiles a sequence of tokens, a sequence of Rust tokens into the AST for our NOC language, if you know what I mean. Right, and it allows us to actually define them like that, which is pretty sweet, not gonna lie. It is in fact pretty sweet. So let's actually do a committee. And maybe even a pushy. So replace fun and sim macros with expr. Right, I'm going to push that right into the repo. You can find the source code of the thing we're developing in here, right? And if you're watching on YouTube, you can find this thing in the description. I'm going to put that in the description just for you. Here it is. This is the source code of the thing that we are developing, right? All right, does anyone have any questions so far? So macros are actually pretty okay, I think. So I kind of like Lisp macros a little bit better, but these one are also fine. So do we have any questions? There are differences between macro brackets types. A curly brace is treated differently in terms of needing a trailing semicolon. Interesting, I didn't know that. Thank you. So we should make a smart contract sometime, I guess. I actually was thinking about getting into Ethereum for, you know, for educational purposes, because I know almost nothing about cryptocurrencies and blockchains. So it would be actually kind of interesting to write the smart contracts for Ethereum blockchain. So I was thinking about that actually. I find macros in Rust very hard to debug. Printf debugging is the only way I could find. Well, yeah, I don't know. Does anyone debug Rust code differently other than using printf debugging? Is Rust code even debuggable with any external tools? I know that you can probably use GDB to debug a Rust program, but does anyone actually use that? Right? I'm pretty sure, I feel like everyone who debugs Rust, they just do printf anyway. So, I don't know. You could also add a macro from rule 2. Yeah, that's actually a pretty cool idea, I think. Right, we can, yeah, we can define a macro for rule as well. Though defining rules like that is already, you know, sufficient enough, but I don't know. Can you do FGKB? I'm pretty sure I can, right? I'm pretty sure we actually taken into account all of that, right? So because it's a recursive macro, right? Like, why wouldn't that work, right? It's a recursive definition. Of course it's gonna work. B not found in the scope. Oh, okay. So you have to wrap it in expression. As you can see, it works perfectly. You can even nest it like so, and it's still gonna work. It's a recursive. That's the point of recursive definition. Cool. So yesu, kawaii freaking desu. So it's kind of like this macro is kind of useless, right? Because it doesn't really add any functionality to the main application, right? But it's kind of useful in terms of in terms of debugging, I suppose, right? So if you want to just define something while developing this language, you can just like define this thing and don't think about it too much. So it's pretty cool. So how much time do we have? I only streamed for 1 hour. Maybe I'm gonna have enough time to implement something actually useful. For instance, a runtime parser of this expression, if you know what I mean. So that would be actually kind of cool. But maybe I'm gonna do that after this, after a simple break, after a small break. But yeah. All right. So. Okay, oh my god, the chat is moving too fast. Can you use macros from text you read from a string, for example? I think you can. I think there are ways to like parse a string, but I'm not sure 100%. I'm not really that proficient with macros. I can only like define simple things with macros. I'm subbed because I can't still join Discord. You have to actually connect your Twitch account with your Discord account. As soon as you do that, the Discord is going to automatically assign role to you and give you access to Discord. So if you can't get the access, you probably didn't connect your Twitch account, or maybe you connected a wrong Twitch account. So that may happen as well. So double check that. Anyway, let's make a small break, and after the break, we're gonna try to implement the parser from a string, like a runtime parser, because I want to be able to define the rules inside of a file and then load up that file into some sort of like REPL and apply all of these rules in runtime. So that's pretty much the goal of this entire application. All right. So let's make a break and all right, so we need to continue developing our knock, which is essentially like expression transformer. We already defined the AST, and we defined a simple macro that allows us to construct the AST at compile time and stuff like that. But constructing ASTs at compile time is not really a useful feature of this entire system. We need to be able to construct the ASTs at runtime, aka being able to parse them, right? So I want to be able to provide a string or provide a file and load up the ASTs from there, right? So that's what essentially we want to do. And Dorn, thank you so much for 2 months of tier 1 subscription. And so yeah, we just need to go ahead and implement that. So the first step of parsing these sort of like a nested tree-like expressions is tokenization, right? A token is a group of characters, right? It's like a group of sequence of characters that is classified by a particular class, right? So essentially, if you have an expression that looks like this, right, you can classify. Let's actually take something more complicated with longer names and stuff like that. So something like this. It's not particularly complicated, but it just like has longer names. So the process of tokenization is going to be basically identifying this group of characters and saying that this denotes a symbol, right? Then we encounter open parent, and we also identify this group of symbols as open parent, right? Then we have a pair, which we also identify as a symbol. Then we have another open pair, right? Open parent, and so on and so forth. So this turns into this sequence of tokens, right? And then having this sequence of tokens, having this group of characters, we can now turn them into AST, right? So we could probably try to parse that without any tokenization, but tokenization actually sort of like helps to parse that a little bit more efficient. So you don't have to think about skipping white spaces because the white spaces are already skipped after the tokenization. You don't have to think about grouping the names and stuff like that because they're already grouped. So essentially tokenization is a pretty useful step in parsing. So let's define a data structure that denotes a particular token, right? So we're going to have a structure, And this is going to be a token, and this structure is going to contain the text, the sequence of characters that was classified as something, right? So it's going to be text string. Confix21, thank you so much for subscribing at tier 1 for 5 months. Thank you, thank you, thank you. Right. And we also want to be able to keep track of the kind of the token, right? I already mentioned the kinds of tokens like symbol, open parent, close parent, comma, and so on and so forth. So let's define enumeration and call it token kind, right? So, and the token itself is going to have the kind, which is a token kind. Right, and in here we're going to have things like symbol, right? So this is a symbol, open parent, close parent. What else do we need? We probably need comma, right? So we need comma, and we probably need equals, right? Maybe we need something else as well, but that's the only thing I can think of so far. So we have like a token kind. All right, so maybe in the future we're also going to have some sort of a location, right? But we're not keeping track of the location yet, so I'm going to just keep it like that. Let's try to compile this entire thing, and as you can see, it seems to be compiling. Right, so now we need to define an entity that would take some sort of like a source, like a sequence of characters, and turn it into a sequence of tokens, right? As already mentioned in the first episode of Knock, I wanted to make the Lexa an iterator over tokens, right? So let's actually define Alexa. All right, and one important thing that we're going to have in here is implementation of an iterator for Alexa, where the item of an iterator is going to be a token, right? You see what I did in here? Right, so that's what we're trying to do. Okay, let's try to compile that, and we need to implement a next method, right? So we need to implement the next method. So in here, the next should return just the token. There we go. So that's what we have in here. It's pretty cool. So now I also need to be able to construct Alexa out of something, right? And I suppose I should be able to construct Alexa out of the iterator of characters, right? So let's actually do from iter, and in here we're going to have a source, which is essentially an implementation of an iterator, right? Implementation of an iterator where the item type is equal to a character. So we accept the iterator over characters, and we return Alexa, which is iterator over tokens, right? So that's basically what it is. And of course here we have to return self. Okay, so, and I don't really know how we're gonna construct that yet. So maybe we're gonna actually make Lexa generic, right? So it's going to be basically parameterized by the type of the iterator of characters that it's processing, if you know what I mean, right? So we're going to have something like characters, and that thing is an iterator, over characters like this, right? And we're going to actually store that thing within that specific structure. So in here I can say it's a characters, and of course I'll have to do something like this. So this is going to be chars, and here we just accept the chars, and that way I can simply construct it like that. Make sense? Hopefully that makes sense. All right. So, and because of this, I also have to probably put this thing in here, because unfortunately Rust is verbose like that. Can't really do anything about that. So it's actually called charts rather than char. It is in fact called chars. Okay, so everything seems to be okay. So now we should be able to do the following thing. Let's imagine that we have like a swap pair A and B, but it's actually a string, right? It's actually a string, and the string slice can be turned into iterator over characters, right? So it's actually chars method. So let's actually take a look. So we take a look at chars. So it's a method of the string slice, which must return, just a second. So the page needs to load up. It returns chars, which is an iterator over characters. So that's how we do that. And then we can construct Alexa out of that iterator. Right, so here we go, we have Alexa. And then we should be able to iterate tokens within that Alexa and maybe even print them. Like so. So this is what we should be able to do. Because the Alexa itself is an iterator and you can use for loops on the iterators. Alright, so let's take a look. So what do we have in here? So the token is supposed to have the debug thingy implemented, so let's actually derive debug. So here's the debug, and here we're gonna also put debug. Okay, and it panics at line 209. Okay, so we just basically need to start implementing this entire thing. Right, so how are we gonna be parsing all of that? Right. So we need to take a look into the first character, right? We need to take a look into the first character. If the first character is open parent, we have to classify this as open parent token, right? If it's let's say if it's a alphanumeric value, we have to continue pulling the characters out of the characters until we encounter something else. Right, and that act of like pulling out until we encounter something else requires actually like peeking into the next character without removing it from the iterator, right? So I may actually start implementing and then we'll see how it goes. So I can take the characters, right, and I can take a look into the next one. And in this particular case, we have two situations. Either we have something, right, either we have the characters in here, or we have nothing. In case of nothing, we can just return none, right? But in case of something, we have to match it against several things, right? So let's take a look at what kind of things we have. We have open parent, so it could be just open parent in here, and in that case we can just return a token, open parent. Though, interestingly enough, we'll have to initialize the token kind and the token string. So we can sort of actually do the following thing. We can take a text, which is going to be immutable, and we can define a string new like this. And we can push X right away. If this entire thing is open parent, we'll have to return some token where the kind is equal token kind open parent, and the text is just equal to the text, right? So there we go. So if it's a close thing, we have to do close parent, right? So it's going to be close parent. Then we're going to have a comma, right? So this is the comma, and then another thing we have equal, and then we have something else, right? Neither any of these four things. Neither any of these four things. And if it's something else, right? If it's something else, what we have to do, we have to continue pulling things until we encounter something else, right? So it's going to be while let some, like another X, and it's just going to be something like self-character next. Self-character next, and if X is alphanumeric, so I think we have to call is alpha numeric, right? So it's alphanumeric like this. Where is the alphanumeric? Here it is. So this is alphanumeric. X is alphanumeric. Numeric. If it's not, we're gonna break out of that. But if it is alphanumeric, we are going to push it into the text, right? And here's an interesting thing. As soon as it becomes not alphanumeric, right, we're gonna stop the loop, but at the same time, we're gonna lose that not alphanumeric, right? Essentially, if we have something like foo, right, we keep pulling characters out of the token, and then we encounter this thing which we removed from the iterator of characters. but we want to be able to keep it inside of the iterator for the next sort of call of the next method. So we need to push it back. We need to push it back after we sort of like stop the recursion. But it's not really possible with the current iterator. And because of that, we have to use a pickable, right? So essentially it's an iterator wrapper that can pick into the next token without removing it from the iterator, if you know what I mean. So pickable. So it's a special iterator wrapper which extends the iterator and introduces pick, which is like next, but it doesn't remove the element from the iterator. All right. So because of that, we have to say pickable characters. There we go. And you can always convert any iterator into pickable iterator by just calling the method pickable. All right. So let me see the following thing. All right. So the cool thing about pickable is that it has next if, right? So it can basically check. Maybe we don't have to use pick in here. We definitely have to use next in here, but we have to use pick in this specific loop, right? So we can do something like next if x is alpha numeric. Okay, so this is actually pretty cool. So that means we can now move this entire condition inside of this thing. All right, that's cool. And this entire stuff returns options. So that means we are basically continue doing this thing. Let some x, and then it returns the x, and we keep pushing it there. And that is it, actually. I think that is it. Can't really think about anything else. Yeah, this is literally it. So now we can construct some token kind what? So it's supposed to be a symbol, right? So this is a symbol and we just provide the text. Okay, so that should be it. Now let me take a look. So here we have a pickable, so it has to be characters, right? So the next thing is what? So if I got a semicolon, that is fine. So what's going to be the next thing? So pickable cannot be found in this specific scope, and this is because it is defined in std_iter pickable, right? Use std_iter pickable, right? So this is what we have it in here. Okay, so the next thing, so we have fun args, which is unused. I think I should mark this thing as like allow that code, right? Because it's a little bit annoying. Or maybe I can just allow unused macro, right? So let's go ahead and just like allow that. So I'm gonna allow that, then we're gonna allow that. Right, so what else do we have here? So equal, so it has to be called equals, right? Okay, so as you can see, we successfully tokenized the expression. So we have a symbol swap, we have open parent, and this thing is another open parent, then comma, then close parent, and close parent. So we essentially have a sequence of tokens that we can then process and turn it into AST, which is quite cool. But I think we do not handle a very important thing in here. I think we don't handle the spaces, right? So, and this is quite important. We don't handle the spaces. So there should be also a very important thing in here. So if text is actually empty, maybe we can do even is empty, we have to throw some sort of an expression, right? not really expression, but a panic, right? So panic, unexpected token, right? It would be nice to actually properly report the position of this thing, but I think I'm gonna do that a little bit later. So I'm gonna just put to do report an expected token properly, right? So this is gonna be a to do. Okay. So, and it went fine, but it was actually a symbol, which is rather interesting, So it was not empty. All right, so I think we have to do something like that. If the current x is alphanumeric, right? If it is alphanumeric, but it's not alphanumeric, we are going to report an expected token, right? We can even say something like an expected token starts with x, right? So an expected token starts with x, and yeah, as you can see, starts with like space, but we can't really see anything, so it would be nice to actually wrap it in quotes, right? And you can't really see that, but yeah, so it starts with that. Okay. Does anyone have any questions maybe so far? Okay, I don't see any questions. Cool. Now, let me see. So we need to handle white spaces properly first, I suppose. So we need to trim them. And we need to trim them in here. So while let some self characters next if x is space, right? So we can do something like that. So while we have spaces, right? While we have spaces in front of the stream of characters, we're going to be just removing them, and then we're going to try to take the next one, right? And if we have something there, we're going to just do that. All right. So what do we have in here? I suppose we have to actually do it like that. Is that what it wants? Method not found. I think it's something is white space. Is it called white space? Yes, it is white space. Is white space. Okay, cool. So as you can see, we handle all of that with spaces. Isn't that cool? I think it's pretty cool. I think it is in fact pretty cool. And since Lexa is iterator, you can quite easily just turn it into a vector of tokens and just basically say, okay, Lexa from iterator, and then collect, right? You basically collect this entire thing, and you can say print like this, tokens. Look at that. And it will just, yeah. Now you have a vector of tokens. So now you have a vector of tokens. More abstractions, more different interfaces. Make the standard library as overcomplicated as possible. Anyway, so we have a tokenizer. So now we need to be able to construct an AST from this basically Lexa. Okay. Does anyone have any questions? I don't see any interesting questions in the chat, so everyone understands what I'm doing, right? Okay, so no questions, I suppose. All right, so we need a function that essentially can parse the Lexa into a particular expression, right? So we're going to do parse. And in here, we're gonna accept Alexa. We can just accept Alexa, immutable Alexa, or maybe you just like move it inside, basically consume it. But I think we can go a little bit more abstract by actually taking the implementation of the iterator over tokens, right? So we take the iterator over tokens, and it does not necessarily has to be that specific Alexa. It could be something else, right? So we're taking just like an iterator. And in here we have to return an expression, right? So it would be nice to have a result, right? But for now, I think I'm gonna just panic if we encounter something unexpected, right? And then later I'm gonna implement like a proper result, like in here. So here we're supposed to probably return a result, right? So here we return an option, but it would be nicer to return a result, right? So to propagate it properly. But for now, I just panic, right, with the to-do, indicating that I need to do something here. So, and I'm gonna do a similar thing in here as well, right? Okay, so here I have Alexa, and then I can try to parse this entire thing. So do I have implementation for a particular expression? I actually don't. So I think what I need to do in here is just do implementation expression, right? And here I'm gonna essentially just accept this thing here, if you know what I mean, right? So this is what we're gonna be doing in here. So this one is self. This one is self. Interestingly, I think I also want to be able to peek into Alexa, right? So I would say that I want to accept a pickable, though I can wrap it into pickable already inside internally. I don't think I have to like do it like that, right? I think I can make it pickable later. All right, so in here I can have Alexa, which I can construct from the iterator, and then I can do something like expression parse, right? Expression parse, which then I can maybe print like so, right? As you can see, right? Does anyone have any questions? So no questions so far. Good. So everything is clear. Okay. Everything is clear. 13. Okay. So again, I need a pickable iterator. I need a pickable iterator. And how can I implement that? So might as well have an internal function somewhere, parse pickable, right, which will essentially accept Alexa, but a pickable, right, and it's going to be essentially this iterator, right, something like this, and it's going to return self. To do. So then it's going to be self parse pickable and Alexa pickable, right? And we just return it like that. Okay, so let me see if it's gonna work. So it's gonna be 13, and it seems to be working. Cool. Now what I need to do is to get the next token, right? That's what I need to do. I need to get the next token. Alexa next, and in here I'm gonna have either something, right, some, and it's supposed to be a name. It's supposed to be a name for either symbol or a functor, right? So let's call it a name. Otherwise we reached end of Alexa, right? And we can't really do anything. So in here I have to say report end of file error, right? So then what specifically we expect in here is maybe I can even match that. So name kind, right? And the kind is supposed to be token kind symbol, right? It has to be token kind symbol. If it's not a symbol, it is also an error, right? Report expected symbol, right? Might as well actually do something like that. Expect symbol. Cool. So here is the symbol, and once we got a symbol, we have to pick into the next token. You know why? Because if the next token is an open parent, that means this is a function call. If the next symbol is not open parent, that means this is a symbol. You see? So how do you distinguish between like a symbol and a function call, right? After a name of a function call, you have a parent, but after the just a symbol, you don't. So and that's how you distinguish them, and that's why we need to have a pickable lexer rather than a regular one, right? Because we want to be able to look ahead, check that you have an open parent, and if it's not open parent, we want to leave it as it is because it might be important for the next phase of parsing. You see what I mean? So yeah, that's essentially the reason why we need to have a pickable situation. All right, so, and let me try to just do that. So this is going to be Lexa, and I'm going to pick into that thing. All right. And we can try to basically match it, I suppose, right? So we can match it if it's... Oh boy, this one is interesting because... So it could be either some next, right? It's basically some next, and if it's not some next, we have to return just none. This one is actually quite annoying because we also need to check that next. How do you parent match the record or the structures? I forgot how to do that in Rust. Parent match struct. Parent syntax. Parent syntax. I wish my computer worked a little bit faster. Right. I should probably buy a new computer. But unfortunately, it is not an option for me anymore. Imagine, like, this computer is like almost 10 years old, and I was always thinking, oh, I'm gonna buy a new one soon. And I just can't. So there's no computers anymore. Elbrus Braid computer. I mean, even Elbrus was actually built in Taiwan, so there's no Elbrus as well. So. Do you get paid for ads? No, I get paid nothing. I get paid literally nothing for what I do. I just do that for fun. Yeah. Is Rust worth the effort to learn? Depends on what you're trying to do. If you're learning Rust to get better at Rust, I think it's worth it. But that's about it. Anyway. So, structure. Okay, so, yeah. I think I should be able to do something like token kind, and then symbol, and then I don't care about everything else, right? So that's essentially what I can do. Though I can try to get the text. I can try to get the text, right? So here is the... Oh no, it's actually open parent, right? Open parent. And then I don't care about everything else. I think I should do next if. Yeah, I should do next if. Next if, and the condition is, so here is the token, t, kind has to be equal to token kind open parent, right? And then if let sum this, here we have to parse the arguments, right? Parse functor arguments, right? So that's what we have to do. Otherwise, we just have to return it as a symbol, right? So we have to turn it into a symbol. Expression, symbol, and we just take the name text, and that's it, basically. Yeah, so that should be it, I think. And here we have to parse the arguments. Okay, so what do we have in here? Token cannot be applied to token kind. So that means I have to go to token kind and do partial equality. Right, so this is going to be the partial equality. So something cannot be borrowed in here, which is rather weird, I suppose, because this thing is supposed to be mutable. Is that what you want? That's kind of weird. Though, maybe I have to, like, pass it as a mutable thing. Can I pass it as a mutable thing in here? I should be able to. There we go, so it panics. But the question is, where does it panic? It panics at parse functor arguments. Okay, that's cool. So it panicked precisely in here, so now we should start parsing things. We should start parsing the things. So we need to prepare a vector for the arguments of the functor, you know what I mean? So this is going to be args, and this is going to be just a vector. And after that, after we're done parsing everything, we should construct expression fun, name text, and we move the arguments in there. So that's going to be the final sort of thing. Semicolon, of course. Yeah, there we go. Okay, cool. So how are we going to be doing all of that? So I probably should check if the next token after that is a close parent. Right, so I can do it like that, I suppose. If this thing is close parent, right, if it is a close parent, we have to just return it, I suppose. Right. So interestingly, we just have to do that, like right away. Yeah. Otherwise, we have to start trying to parse the expression, right? So trying to parse the expression, and then look for comma, if that makes any sense. So let's do something like this. So this is going to be arc. Parse pickable, right? So this is a parse pickable, and we provide the lexa. So we parse the first argument, right? We parse the first argument, and we need to push that into the list of arguments, right? And while lexa next if t kind equal token kind comma, right, while this is still a thing, right, we need to repeat this entire stuff, right? We need to repeat this entire stuff. Maybe we need to just do it like, though interestingly I can just do it like that, right? So I can just parse the next one, and oh my god, and then the next one in here. So as soon as I encounter something that is not comma, what I need to check in here is whether it is a close or not, right? So if the next token is not close, we have to say something about that, right? So lexa next, right? And if let sum so it has to be token kind nothing. But I have to kind of do like an opposite thing, right? So so I'm not really sure. So here token, right, to do, but if we got nothing, we have to do something like expected close parent but got nothing, right? So expected close parent, but got nothing. And in here, we're gonna have token kind not equal, token kind close parent, right? Token kind close parent. We have to do expected close, not parent, but parent. Close parent, but got something else, right? So something like this, right? And after that, we're gonna have something like this. I feel like you can simplify that. But I'm not 100% sure. So if you have like Lexa next if, right, and T must be token kind close parent, right? And if it is none, right, you can basically maybe collapse both of these things into a single one, expected close parent. Something like that, I guess. I guess you can do something like that, right? Maybe that makes sense. Anyway, so that should be it. Let me see. Parse pickable, not found in the scope because it's a part of the self, right? It's part of the self. So this is another one, part of the self. And what else do we have in here? So this thing is supposed to be mutable. Let's make it mutable. And what do we have? We just successfully parsed the string. So this is what we got. So this is the input that we were trying to parse, and this is the AST. So we just successfully parsed the string, the AST of string. We can try to print it as not debug one, right? So as a not debug one. And yeah, that's literally what it is. So we implemented sophisticated remover of spaces. Sophisticated remover of spaces, which is kind of cool, isn't it? I think it's kind of cool. Interestingly enough, now we can even try to apply different rules on this entire thing. Right. For instance, you can take that, and then if you have a rule, right? So here is a swap rule. We can do print ln, right? So here is the, let's call it like this. So this is going to be source. This is a swap, right? So this is a swap. I take the source, I turn it into characters, then I parse it, and then I can take the swap rule, apply all, right? So this is apply all. Might as well just take it like that. We need to do that. So here's the original source, right? Then I apply everything, and then I try to print that, like so. So it does not really work properly. Characters is not in the scope, okay. Okay, so what else do we have in here? So it's supposed to be a reference, sure. I can make it a reference. Okay. So this is pair, right? So this was the original source, right? Just a string, We tokenized it. We then parsed it, and then we applied the rule which swaps the arguments of the pair if we have a swap functor over it. So essentially we have all of the necessary parts to build the entire system. Right, so we have an engine that can pattern match the expressions and actually apply the rules, different rules. We have a tokenizer, we have a parser, so we can actually put this stuff into a text file. So the engine is ready, we just need to make some sort of a user interface, right? The user interface that can read the inputs, some different inputs, and, you know, apply the rules and whatnot. So that's actually pretty cool. What do you guys think? I think that's pretty cool. Okay, so maybe I need to organize the, I don't know, the repo. So let's go ahead and do a committee. So let me see. Okay. Implement expression parser. Right, so we have an expression parser, and I'm going to push that right into the repo. So how are we going to be doing all of that? How are we going to be doing all of that? I don't quite remember. So we probably have to use like stdin. Rust read line from user input. I remember how to do that. How to get the user input. So let me see. So probably have to use like stdin and then have to lock it and then read the line. And this website is very slow. Okay. So stdin read line, you read it into a string. Okay, so a string, and then you, okay, so that makes sense. Okay, cool. All right, so let's go ahead and do that. Now, so I can probably, I'm gonna keep the swap rule in here. So this is gonna be prompt, maybe command, string new. Right, so this is going to be string new, and then I'm probably going to have something like mute quit false, right? While not quit, right? We're going to have stdin, right, read line, and then mutable command, right? What we're going to have in here, might as well actually print something like this, right? It's probably without this stuff. But on top of that, I think we need to, we need to flush std out, because if there's no new line, it's not going to be flushed automatically. I'm not really sure if that's important, but that's fine. Okay, so we read that, and the next thing we can try to do is essentially parse this entire thing. We can do lexa, right, lexa from iter, then I can take command, and I take the characters, right? Then expression parse, and that gives me the new expression, which I can just, I think for now I'm going to print it, right? I think that's the easiest thing to do now, right? So this is going to be just that, which is going to print the expression. We're not going to try to apply any rules yet, but we're going to just print it just to see how it goes. So now I'm going to just build it. Okay, let's see. So std out, I suppose we need to use stdio, stdin, and std out, right? So that's the thing we need in here, I suppose. Lexa, yeah, that's one thing. So it wants stdio right for this entire thing to work properly, sure. Okay, okay, it built. Now, let me just go to here. So this is knock, and then I'm going to cargo run. Okay, so it's doing things. Can I do A? Okay. F of... oh shit. A. F of A. Okay, it didn't work. That's really strange. I wonder why. If I try something else, if it's gonna be B, it is B. If it's A, it keeps the same. So it feels like maybe I have to clean the command every time I actually do that. But that's, I'm not really sure what the hell is going on. So maybe I'm gonna do it like that. So let me see. So this is the input. So maybe it has something to do with new lines, but I'm not 100% sure. So yeah. Get input string. I have a feeling that I have to clean the command. I have a feeling that I have to do that every time. Is it clear or is it not? I don't remember actually, but the compiler will tell me. Okay, so it does work, and okay. So, but that's really strange because it works without that stuff. Okay, so it seems to be working. So if I do B S S, it actually works. But if I have an incorrect thing, it panics and actually, stops the repo, which is fine for now, right? So later I'm gonna actually remove all of these to-dos and just return like a result. But for now, at least we can do some stuff. So the next thing I want to do, by the way, after parsing, I can try to apply the rule, right? Apply all to this entire stuff, right? As you can see, I'm going to try to apply all. This one has to be like this, right? So if I just have A, it doesn't do anything. If I have pair A, B, it doesn't do anything. If I do swap pair A, B, it will turn it into pair B, A, right? As you can see, we have an internal rule that is always applied to any expression that we actually put in there. So as you can see, this entire system is starting to come together, right? We have a tokenizer, parser, and the engine that applies the rules. So we already have that. Unfortunately, the main problem here is that if you provide an incorrect thing, it will basically crash, and we need to do something about that. I wonder. So now I need to think about the interface for this entire stuff. How are we going to be transforming the expression? So as already mentioned before, the main idea kind of looks like this. This is not particularly readable, but yeah. So essentially, you have a bunch of rules like this, right? And maybe I want to be able to read those rules from a file and then provide the expression that I want to transform, and then specify what kind of rules I want to apply to the expressions and see how it's going to be transformed and whatnot. So that's going to be the idea. Of course, we don't support the the binary operators and whatnot, but I'm going to add the support for them a little bit later. But yeah. So that's pretty cool. I'm already streaming for almost 2 hours. Does anyone have any questions? So before I go, I probably need to actually commit this entire thing. Okay. Implement rudimentary. Is that how we spell it? Rudimentary? I don't remember. Rudiment. Okay, so that's how we spell it. Rudimentary REPL, and I'm gonna push that right into the repo. You aren't handling token equal right now? No, I'm not handling. I'm not doing a lot of things. The program is unfinished. In an unfinished program, a lot of things are unfinished. Yes. I suspect one could use transducers to make this really sexy and more modular. Waste of time. Doesn't add any features. Does anyone have any questions? No, I don't handle equals. The program is unfinished. Equals, we only need to handle equals if we parse the rules. Right now, I don't parse the rules, I just parse the expressions. Rule is basically left expression equals right expression. It's very easy to implement. What's important right now is what's going to be the interface? How the user specifies the rules, how the user specifies the initial expression to transform. How the session of transforming the particular expression going to be saved? Is it going to be saved somewhere, or is it going to be something else? I don't know. How do you make sure rules don't loop? I don't apply them recursively. That's how I make sure they don't loop. So I apply one rule at a time. So yeah. I mean, it's a very strange question to define. I mean, I just applied the rule once. That's it. So if you have a rule that is essentially A, like FB equal FB, right? Or maybe even, I don't know, like A. And you have expression FB, which gets transformed into FBA, right? It's not, this one doesn't look. So it just applied once. I don't understand the question, honestly. What happens if you enter equal FA? It will crash because the program isn't finished. The program isn't finished. The program isn't finished. The program is unfinished. Thank you, Chaos Driver, for 6 months of Twitch Prime subscription. Thank you. How are you old? By aging. All right, so I guess that is basically it. That's essentially it. So this implements basically everything. So what I need to do is put everything together, implement some missing features like binary operators and whatnot, and turn it into a system where you can just basically doodle around with the expressions. So, and what I'm thinking is that the next sort of like stream or episode of Nog is going to be me demonstrating the final thing where you can input rules, input expressions and stuff like that, and then just play with it. So yeah, I documented the basic development of all of the necessary core parts, and the rest of the stuff is just polishing this and just putting together, which is not really that interesting. So I think I already documented everything that is interesting in the development of this entire tool, and yeah, I guess that is basically it. And after that I may continue working on Porth, right? So yeah, so it was a small break from Porth, like a little side project that I always wanted to implement, right? So I always wanted to have this small system which allows you to transform algebraic expressions, but it is not Coq, because Coq is a little bit verbose and it's just you know, a little bit finicky. So yeah, that's it for today. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you on the next Zozin session where I'm going to demonstrate the final vision of this program, right? So yeah, thanks everyone. Thank you everyone for watching. Love you all. Stay safe.